Hello everyone, this is Mr. Reese, and this video is going to concern partial fraction decomposition. And to kind of give you an idea of what this is about, what I want to do is start off with these two little fractions here. Let's say you were to take these two fractions and combine them into one fraction. Well, what you would do is you would try to get a common denominator. For this fraction on the left, you would multiply the top and the bottom by x plus 2. For the fraction on the right, it would be x squared minus 3. And in doing so, what you would get is this. That's after you multiply the denominators. That would give you this. And after you FOIL this and distribute this, collect all your like terms, you wind up with negative 3x plus 29. Well, this video essentially is going to reverse this process. With partial fraction decomposition, what you do is you take one big fraction like this and you try to separate it into smaller fractions. So let's take that same problem and work in reverse. You will note that I did not multiply together the denominator. Instead, I have it factored out, and that's precisely how you want to start out with that. You will want to make sure that the denominator is fully factored out first before you do anything, because that helps you identify what your fractions are going to look like. Each fraction gets a denominator equivalent to those factors. So one will have x squared minus 3, the other will have x plus 2. And the reason is because if you were to combine this into one fraction, you'd get a common denominator. That would mean multiplying this by x plus 2. That would mean multiplying this other one by x squared minus 3. Now, as far as the numerator is concerned, this first fraction is going to be ax plus b. This second fraction will be c. Then what you would do is you would solve for a, b, and c, and that would finalize your answer. If you're curious as to why we do this, the numerator essentially is just going to be a polynomial. The only difference is that its degree is going to be 1 degree less than the bottom. So this has a degree of 1, so this is a degree of 0. This is a degree of 2, so therefore the degree on this is 1, and then we just simply count downward. If this were, say, x cubed, then you'd have x squared, then x, then constant. Now, as far as solving for a, b, and c, we'll worry about that in a later problem. Let's do another one where we have to try and set it up. So how about this one? You'll note that it's already fully factored out. So we're going to write a fraction for each factor here. So we'll need one for the x plus 1 and one for the x minus 3 squared. I want to make a note, though, that we want to account for when x minus 3 is not squared. That is a distinct possibility, and so we have to account for that. The reason being is that whenever you have factors, you always require a fraction that has a smaller power of this. So if you had squared, you would need one for the first power. If you had, say, to the fourth power, then you would need one for the third power, and the second power, and the first power. The first fraction will have a for the numerator because, again, as far as the degrees are concerned, the degree of the top must be 1 less than the bottom. This is degree 1. This will be degree 0. Likewise for the second fraction. The third fraction is also degree 0, and if you're wondering why, because this is x squared, after all, couldn't you just do this? Well, you wouldn't be wrong in doing that, but it's actually unnecessary. The reason being is because the way we look at the bottom, technically, would be like this, where it's x minus 3 and the whole fraction is squared. So if you look at it from that standpoint, you only need a constant, c, up here. The x plus d is unnecessary. Again, you wouldn't be wrong, but what you would be doing is you would be including another variable in here, the variable x, and that often makes the problem a little more complicated. So we want to try to avoid that. Therefore, that's all you really need. How about we try another? What about this one? Again, want to make sure that the denominator is fully factored first. X squared comes out of both of these terms, so we'll have that out front. Now, let's go ahead and write out our fractions. Just as before, we need a fraction for each and every single one. So, again, since we have x squared, we're going to need the power of x as well. Since it's the whole thing squared, we walk it down and go 1 to the 1 power as well. Here it's x cubed minus 5. This is one complete binomial, so we wouldn't go x cubed, x squared, x. And again, it's not the whole thing that's cubed, but rather just the term within this binomial. And this would be your numerators. Remember that the numerators are 1 degree less than the denominators. So this is degree 1, on top is degree 0. This is also going to be degree 0. And you're looking at this and thinking, well, that's degree 2. How come it's not bx plus c? Shouldn't it be like this? Again, this actually isn't wrong. You would be technically right in this, but we would be doing something that's unnecessary, which is to add in another variable. When you do this, this does make the problem a little more complex. So that's all you need. The way to think of x squared is to think of it as x minus 0, and then the whole fraction squared. If you think about it in those terms, then it becomes a little obvious. This has a power of 1, so therefore on top, you would need just a constant. Okay, so now let's do an example. Write the partial fraction decomposition of this fraction. Just as before, we want to make sure that the denominator is fully factored. So 2x squared minus 7x minus 4 simply becomes 2x plus 1 times x minus 4. So when we write this out with our fractions, each factor gets its own fraction. So the 2x plus 1 and the x minus 4 are on the bottom. And remember that on top the numerator is 1 degree less than the denominator, so we'll just have a and b. Since this is the first power, this will be to the 0 power. So now that we've done that, let's go ahead now and try to determine what a and b are. First thing we want to do is multiply out the denominator, because working in fractions to solve a couple variables here, it's very difficult. So the denominators are 2x plus 1 and x minus 4. That's when it's fully factored out. And use this here as a guide. What you'll do is you'll multiply both sides by this. So what happens essentially is that here on the left-hand side, they just completely reduce out. And on the right-hand side, what you're going to need to do is you're going to need to distribute. So go ahead and take this whole thing here and distribute to this fraction on the left and this fraction on the right. So let's just look at that part here. If you do that, what happens is you get a reduction just for one of these. Same thing over here, just for one of these. Whatever you have left, you're just simply going to have to multiply it together. So go ahead and take this x minus 4, multiply it to a, or rather take the a and distribute. Same thing for the b, take the b and distribute, and that's what we wind up with. You get ax minus 4a for this first one, that's this guy, and 2bx plus b for this second group here. Alright, now let's go ahead and collect our like terms, but when we do this, we're going to be doing it according to the powers of x. You'll note that this has an x and this has an x. So these two groups will collect together, and as far as the other two is concerned, neither of these have an x, the negative 4a nor the b. So you're seeing that here together. Thus, what we're going to do here is, for this first one, we are going to factor out the x, so we wind up with this. And since this is its own grouping, since they're all constants, it's going to be plus the whole group. Now we have this thing pretty much set up for what we want to do. What we're going to do now is we're going to be setting the coefficients equal to one another. What you should recognize is that this whole thing matches this whole thing. Since both of these have x, what that means This means that they are equal to one another. So 11x is equal to a plus 2bx, and the negative 17 is going to equal to this group here. So that's what you're seeing right here. If you're wondering what happened to the x, shouldn't 11x equal to a plus 2bx like I shaded in here? You'd be correct. The only reason why I didn't put the x here in the beginning is because we just simply divide them out. If you divide out the left-hand side by x and the right-hand side by x, well, they just simply go away. So that's what you wind up with. Well, what you have now is a simple system. Just go ahead and solve that system. Use elimination or substitution, however you wish, and that would be enough to do that. So let's assume you can do that. Let's assume you can solve this system on your own. I won't go into the particulars of elimination and substitution. We get our answer. A is 5 and B is 3. And that pretty much completes it. What you do now is this. You just simply refer back to your original setup. The original setup was this. And what you do is, right here, you're going to put 5. And for the other one, you're going to put in 3. And that would be your answer. Now, if you want to go ahead and check, be my guest, get a common denominator here, and then collect this together into one fraction. That would do it for you if you're really feeling uncertain about your work.